Uh, Welcome to the second session for today. As per the schedule, we had planned to have this session as characterization of composites, but I slightly modified this because when I was going through the content and some books which I referred for it, even I came across few resources where some of the processes are categorized only as testing, they do not consider it characterization, whereas some other resources suggest that they can be testing and characterization. So, rather than getting into that loop, I thought let me generalize it with both the titles. Anyway, the content remains the same. Now, the thing is, initially we had thought when we were planning the content, so I had requested Professor Dumitru to plan his content first, and once he was ready with his major contents, then I decided upon my contents, and that's how we finalized, both of us together finalized the entire flow of our presentations. Now, in that case, initially what we had thought was we will talk about, say, when we had a processing class, when we had a session on processing or say 3D printing. So, we initially thought that we will put up only the processing part or the printing part into it. Now, you talk about the experiments that you are going to conduct, what materials you used, what parameters you studied, and then you do not discuss the results into it. Just as we have our thesis, we talk everything about plan and procedure in one chapter, and we talk about result and discussion somewhere else. So, rather than that, even our flow was defined that way, but later on we found that it does not give the right feel. So, at some point of time when you again discuss the results, maybe it is possible that we may have forgotten, and that usually happens. We may have missed the procedure part or the experimental setup part. So, those things were shifted later on, maybe in the later part of the last week only. So, now this title should slightly get revised, but because I did not wanted to make it too much of changes. So, this should become a generalized statement like testing and characterization of materials, or so should I keep composites or not as per the title. So, I added materials into it. So, I also thought of putting polymer and composite materials, but then it would have been too long, and so I resist myself from changing that. So, our present session would be more towards discussing the testing processes and characterization processes. So, this might seem as a session wherein because most of us are in the same boat, so we might be doing many of or few of these processes. Some of the discussions which we are going to have, we haven't tried at our end. Most of the other things we have tried. Similarly, it may happen that at your end also you may have tried few of them and maybe planning to try some other at a later stage. So, this would be more like a summary session and just a revision sort of thing for all of us. In this particular session, I am very much thankful to Arjun in absentia. He has put up good efforts in compiling the information, not only compiling the information, but looking for the best possible videos for it, which are short and sweet. So, that is how that was a bit of introduction to this. So, we know composites are reinforcements plus matrix together. So, that gives rise to composites. Now, what happens over here is as per our previous discussions, often fibers contribute more towards the strength rather than the whatever matrix, whatever polymer we use. So, when we try to go through mechanical testing, we have an idea that results may come out to be in particular trend based on our exposure to the literature. But now what happens is, when we try to characterize it, when we try to get deeper into it, when we try to study the microstructure into it, there are n number of things which may be affecting that particular value of strength. So, when you get a quantitative value, there are many qualitative issues into it which contribute to that value. So, sometimes you must have seen or you must have come across a situation wherein we try to report something and we find that in literature they come up with slightly different trend. So, when you only put up the quantitative values, those trends may slightly differ when we compare with our results. The results may be n number of things. The way we have made a composite and the way somebody else makes, there would be some difference into it. Now, just imagine the demonstration we had yesterday, when we try to infuse the resin in a vacuum bag and then we allow it to cure. Definitely today's weather will have its effect. Since yesterday evening the weather has slightly changed, and because of that its effect will come on it. Now, that is a noise factor, we do not include it in our consideration, and once we go for testing we forget also what was the situation on the day of curing. So, that may not be the case with somebody else. So, the way you fabricate a part and test it at certain place, you do not have control over the environment. Similarly, there are many other factors which come into picture. Even same type of raw material, if you are procuring from different sources, you get some different result. That is also one of the vague observation which we have made. So, only quantitative value often leads us to some sort of error. I remember in one case, in one of review of one of our paper, the reviewer doubted our results. I do not say that he doubted our efforts, but he had doubts on the results, and he put up he concluded all his confusions into it, and he suggested that why you get this result, I am not able to agree to it. So, what we did was we measured those things again, we recorded it, we video recorded it, and with our reply we attached the video, and after 6th review that paper got published. It took almost 2 years to publish a paper. So, now when you see that paper, you find that okay, submitted on so and so and accepted on so and so, there the difference comes out to be almost 18 to 20 months. So, the thing was, a value can always be doubted. Just because the machine changed, the way that machine was able to measure something was different. So, often it results into some sort of confusions when we only concentrate on quantitative value. Now, that happens more when the part is composite, because it can have natural fiber or it can have man-made fiber. It can have particles. Particles can be nanoparticles, they may be conductive, they may be magnetic, they may be something else. You may be mixing two polymers if you are going for SLS process, and those polymers would have their own individual way of behaving with temperature, with heat. So, n number of possibilities you come across. So, if I talk about nylon as a 3D printing material and nylon as a whole which I get from the market, both will show, the range would remain same, but they will show different results to me. Now, when I want to make a comparison, often trend line does not match. So, when you see the papers which are polymer composites through 3D printing, you will always see that your trend lines are quite different. Maybe you can refer Raghav's report in the lab. He has put up graphs. The other guy, maybe Janish or someone, not Janish, maybe Arjun has put up the stress strain curves, and if you see those curves, everything is totally different. They do not come across a single trend. Same material, the exposure time changed, the way you exposed them for curing, that changed, and a large number failed because of that. Now, that you cannot put up in a paper. So, in such situations where a value does not help us to conclude some result, there characterization comes into picture. So, if you go into microstructure, you get into the structure yourself and just try to observe it, it may give you the results. Okay, something delaminated, something got pulled out, there was no affinity between these materials. Those things if you see, you probably are able to make a good judgment with the value that you get through the measurements. So, in such situations only focusing on say mechanical testing may not be. Often we feel that okay, I did all these things which is there in so and so paper, somebody has done all these activities, I did the same thing, I did 2 more tests than them, but still my paper did not get accepted. Why so? But probably the reviewer wants something to substantiate our results. So, there this characterization one or the other way comes into picture. Nowadays, because of the grants which DST has been dispersing everywhere, good facilities are coming up in almost all regions. So, we can easily utilize those facilities to get some characterization results and maybe include in our work. So, when we talk about the testing of the materials, we largely concentrate on quantifying the physical properties or mechanical properties, and these values in most of the cases comes through mechanical loading. A part is loaded mostly on the axial direction, and because of that the deformation that occurs, it gives certain results to us, whatever be the process. In all those processes, we are required to load the specimen under mechanical action. So, our intention is, and there in that case in almost all the processes there are standard specimens, standard dimensions. Of course, they have certain range of dimension into it, but those are standard dimensions and it is expected that those results that we obtain, similar way the material would actually behave when it is put in the application, right. So, that is why we intend to carry out this mechanical testings. Now, as compared to that, when we talk about characterization, we not only restrict ourselves to those properties, physical or mechanical properties, but we go beyond that. We want to not only measure, we want to assess the internal structure, we want to assess the performance. And when we go into internal structure, we mean to say that there can be the way in which the heat flows into it, the way in which the molecules are arranged into it, the way in which the grain boundaries are defined, the way in which the electrical conductivity takes place, the way in which the structure behaves, maybe under impact or maybe under continuous load. It can be anything, but the thing is we want to assess the situation that we are not able to see through our naked eyes. So, along with physical properties, we also concentrate on the chemical properties and the microstructure of such parts. There was one interesting result yesterday which we had discussed, how a fiber, continuous fiber was put in in between polymer. When we wanted to print it, when we wanted to pass them separately through the nozzle, and we observed that ideally the fiber, continuous fiber should be covered by the polymer, but through some microstructures we observed that it remained on one of the side, and because of that, that becomes a place where it can fail, because it is easier for that fiber to move out, get pulled out from the polymer. So, that we come to know when we see it. Had there been a situation where because of any reason the fiber was perfectly placed at the center then it would have given a different range of the strength values. So that difference is visible through such microstructure analysis. So when we talk about all the processes which I want to discuss right now, I am just trying to put them under 3 different banners. This is not the only way in which we can classify them, but the way I have put up in the further slides, this is how I have tried to combine. So I wish to talk about quantitative methods and qualitative methods. Non-destructive is something which I am not touching about. Okay. So altogether that can become a separate session. So that is something which I am not discussing in this session. So these are different things which again there are many more processes which can be included into this list, and but few of them which I wish that that are the processes which are being referred regularly in recent times. So we tried to include those techniques. So largely they are mechanical techniques, thermal analysis, conductivity testing, moisture absorption. Fatigue test is something which is again something to debate, and I had debate with my friend that why don't we put it under mechanical testing, and he came, he showed me 2 books, online books, where there were mechanical test and fatigue test. So the only logic which I also agreed was, if so and so professor can say keep it separately, why can't we also keep it separately? So I went with his choice, because yes, but then it comes under that domain only, and that is why we kept as it is, that was available in one of the resource. Now mechanical testing, this would be a revision for all of us, because we have gone through all the processes one or the other time. When we are trying to study the behavior of materials under different loading situations, then we may choose certain processes for certain specific study of mechanical properties. So we may go for tensile testing, compression testing, flexural testing, torsion, creep, hardness, impact, and fatigue. So these are the things which we would largely concentrate on. Now it depends upon what specific raw material we are targeting on, and that particular raw material may have a specific application, and for such an application we may be requiring to go for specific tests. The other day, maybe a few days back, I had a long debate with Janish. He wanted to conduct open tensile testing as part of his MTech dissertation. So we have carried out impact testing as well as tensile testing in his work, and he said that, sir, I have time and there are resources, so let me also go for this open hole tensile testing. So my question was, if you are working on Kevlar, why you want to go for tensile testing? Kevlar is not going to, more or less it has such applications where it has to undergo impact. So if you want to study impact, go into more detail of impact study, why you want to go for it? So then that discussion we stopped, because we got busy with the program. But the thing was, we eventually felt that there was no need to further extend our discussions on tensile study of some material which eventually has a market and has an application in impact study. So even though it is possible, now you can always come with a statement that there are many literatures available on this process and that process, but open hole tensile testing for Kevlar is not reported. This is how we come to the objective, right, usually. So we club up many things, this is done, the other thing is done, but this one is not done, so I will do that. So often you do not find such research being done, so that will not be the ideal situation. So what I wanted to say is that we will have to decide for a specific way of conducting an experiment, conducting a study based on the application of that part. So, in spite of listing down many methods, we for a specific group of materials we may prefer to go for only few of the methods. You were putting up some questions,
yes, sir. I want to know how we can differentiate stiffness and toughness.
I will come to that. So, the first thing is the tensile testing, wherein the strength is the major concern which we try to study, and when we bring in ductility, we also bring in the elongation part, and most of our studies are towards the study of the tensile strength and the elongation that is involved into it. Of course, there are no specific separate standards meant for, say, regular process or the 3D printing process, or maybe only polymers or mixed polymers or composite polymers. But more or less, if you see that there are certain standards which are being followed for tensile testing, and in certain conditions we need to go for a dog bone shape only, and in some cases we go for flat specimens. So, accordingly there are two major standards, D638 and D3039, which are being used. Now, there is an interesting thing that when we go for D3039, and in some cases with a dog bone shape also, we require to put up the cover on the edges. What do you call that cover? Yes. So there the requirement is that it should be made from the parent material. Now, when you go for a 3D printing that part, how you put a parent material on it, unless and until you include it into design of printing. When you put it in the design, then and then you can have that cover. So, altogether when we use that 3D printed part, we avoid going for that, and it is a usual convention. But when you make some parts by some other processes, the same composites, then there it is a requirement, and if you see the literature, they would say that as per the standard we have put up. In our case also we had used emery paper, because the base parent material was getting slipped when we were trying to hold it. But now the same situation when it comes to 3D printing, you do not do it, because how would you create a cover without printing for a printed part? Now, if you include it into the design, then it is against the dimensions that are required. So, those things are always debated. When even I put the same question when I am reviewer for some paper, that why you have not included it, and it is always interesting to go through the answers. It helps because when you are to reply, you have n number of options to reply by getting such replies. So, there are many open ends where there is a possibility that they can work on further in defining the standards. One of these tensometer you must have seen yesterday, no, today. So, there is probably we are going to have some demonstration on one of these machines. So, we have these two machines, one is UTM and the other is electronic tensometer. This tensometer is a very good machine. It came to our department in 2005, and it was the only machine that was not affected by the floods of 2006. Everything else in the workshop and manufacturing section was underwater. It was saved because it was light in weight, so they thought, let us put it on the first floor. So, this was the only machine in our workshop and in our machine tool lab which went to the first floor and was saved. Everything else was in water, including faculties. Since 2005, this machine is working effectively even today. No major repairs, some changes of spares, and we go for regular servicing of it. We go for regular calibration of it. This is a good machine that way, and it is a cheap machine. You get, even today it comes around 6.57 lakhs only.
Is it adding anything different from this?
No, the thing is, it can go up to 20 kilonewton. The load cell is up to 20 kilonewton only. So, it serves our purpose. But you can conduct tensile, compression, flexure, shear, everything you can have. All attachments you can have into it. Yes. that would be interesting to see. They will show you.
And why in some specimens we do that open hole testing? In the
Open hole testing is specifically planned when a part has to have, in the design you have, it is to become part of some assembly, and that part will definitely have a hole into it, so that those fasteners can be attached to it, and that part behaves well, but whenever it fails at that hole only. So that is why for certain applications where you need to design a part with holes into it, so there, other than tensile testing, we go for open hole tensile testing. And then their dimensions are also, there are two different dimensions of the hole also. So there are two different sets of standards for studying it, depending on the conditions that it will undergo. And it was interesting when we tried to study the same for 3D printing. Now if you remember, we talked about the process, we can put up those rings at the periphery, 0 to 5 rings, if you remember I had discussed. Now incidentally, if I select 5 rings, it understands that rings are to be placed at the periphery. So when you put a hole in the center of an open hole test, it considers that also a periphery and puts 5 rings over it. Now when there are 5 rings over it, it reaches both the extremes of the part. So there is no place for you to place those 0, 90, 45 degree inclinations. So for that particular case, we changed our strategy and we reduced that 5 number to 3, so that there was some space. And there were cases where there is an interesting paper by Ashish, wherein this entire central part was covered with those rings, and there were 2 separate parts with 90 degree and 0 degree inclinations. 0 degree, there were 0 degree on one part and 0 degree on the other part with a center in between. So naturally, when the failure occurs, that failure will definitely occur at the boundary of those rings and the rectilinear structure. So that was a wrong selection of design. The way that design was selected, that was wrong.
Or we can go on the other way. Let's print it normal and then we make a hole later. Because in the
Yes.
design you are putting a hole.
Yes, but
The software will infill, put the perimeters there.
but what we thought was, if you are printing something and then if you have to rework on it, then there is no point in having a 3D printing process. So we changed that strategy and then we reduced those number of rings, and then we made the study 0 and maybe 3 rings, I suppose, that we have reported. So often our results lead to change in our strategies. So there the failure was evident. It could be very easily predicted based on the design that was selected. But in the same condition, when you had say 60 number of layers, so you may have fibers in 25 to 30 layers, say up to 50% you want to go. So maybe 30 layers are with fibers. Rest of the layers, if you put them only at 0 degree and with 100% infill, then this result could definitely change. So you change the strategy and you get better results. So now the best conclusion which we derived and which we did not put into it was, depending on what application you have, you should have a dedicated design for it, and you should fix up different layers, different design at different layers, so that you add a flavor of everything into it. So rather than having 45 plus or minus 45 in all the layers, if it is a necessity to do it, if you want to place it around a circle, an internal hole, then that is fine for certain layers. But then you can add some layers wherein you don't put them at any inclination other than 0 degree. So once you have something at 0 degree, it improves the strength of that part. So that flexibility you get when you are using 3D printing, if that may not be possible when you are using any process like VARTM or the other, wherein you have the limitations of putting up the fabrics. So in that case it is not possible. You will have to drill a hole into it if you want to carry out open hole tensile testing. and that would also create troubles, because if there are fibers at that particular position, they would get pulled out. Certain fibers would get pulled out, glass fiber easily gets pulled out, carbon fiber may not get pulled out the way glass fiber gets pulled out. So, that particular way in which you are drilling a hole into it, that will also affect the strength part, the fiber part, yes, yes. Now, suppose if it is 45 or 0.90, in such cases where the fibers are at 45 degree, there the pull out is restricted, but when it is 90 and 0, in 90's case it is very easily, at least 2 fibers will definitely come out, which are on the border at 90 degree, but are falling on the border of the circle. So, they will definitely get pulled out, they would get removed, and probably they may also lead to delamination at some point of time. So, such examples may convey that the strength would get compromised. Okay. Now, it is always interesting, also this is also known to us, that as per the standard there are different ways in which we can prepare the standard specimens. I hope I am not restricting your view. We will be able to select different shapes, different forms of standard specimen, and the way in which the fracture happens usually is in 3 ways. One is a deformation which leads to immediate failure. Sometimes you initiate the necking part and you see the failure. Sometimes necking is extended to a very high value and then we see the failure. In each of the cases we will see a separate type of stress strain curve, and that always is interesting to interpret. But in general this is what we know, the general stress strain curve that is being used. I will not go into that detail. So, these are the 2 different tests that have been performed at our lab. Yes.
So, usually in composites, ultimate tensile strength is only yield, there is barely any yield, right?
Did it break?
Yes.
When it break? Let me see first. Yeah, that's what I was because when I use laptop, I usually keep it off. The voice is off. Interesting, huh? Who did this experiment on natural fiber? The whistle was good, I suppose. So, I think this is the copper infill PLA copper, okay, and this one is the natural fiber, I suppose, jute jute and flex, I suppose. See, the thing is, the dimensions, you get a certain range into it. So, when we are going for the cutting, if you are going with certain size of the fabric and when you are cutting it into the minimum size, then you get only 2 strands of it. You may cut it this way. So, you will get only one of this, only this much portion. So, that will not help us to get the result, the desired result, because it is going to fail immediately, it is going to get delaminated very soon. So, extreme dimensions you can go for. So, rather than selecting this standard, we went for the other standard for it, and that was, we initiated the first result that came up was those first experiments were with the metallurgy department in IIT Bombay. So, they suggested that it is better that you go for another standard as compared to this one, and creating a dog bone shape into this was also not a good idea, because ultimately those are fabrics. So, if you are cutting it at a particular position, there are chances that they may be, those portions may be pulled out easily.
How are they
So, these are cut by abrasive water jet machining. Laser was an option, but what we observed was at the edges those fibers were burning. So, it was turning black on the edge and those portions were getting burnt. And then the other thing that we observed was because this is resin, so that resin also burns and it creates a foul smell also. So, we avoided that, and that was one of the reason. Other reason was that the machine was available with us at that time. So, that was a better choice. Eventually, our abrasive water jet machine went into maintenance, and then we had to seek support from outside, because we had initiated with abrasive water jet. So, we had to use that, and then when we went for outsourcing it, it became even more expensive than the laser cutting. But then you cannot change the strategy somewhere in the middle of your work. Same way for compressive testing, we have different standards. Usually 695 is what we have used. So, there are two different sets of standards depending on what dimensions we produce, and by and large, especially for 3D printed parts, D695 is the standard that is preferred. The reason being that it is the design is simple, the material utilization is less for printing, and you get better parts, maybe faster printing also. So, this is how it goes, and the initial this is the clay part, right, terracotta part. So, initial stage, and that was the final stage after printing. So, usually compression test is not meant for metallic parts. Tensile tests give you the required information. So, compression is largely for those materials which are used into either building applications or maybe in for those that are related to polymers. So, same way you have a standard curve for this process also. Now, we are getting a outsourcing the video for compression testing, because ours were not that clear to put up. In compression, you observe more of delamination as compared to tensile testing. So, breaking of the fibers is often not the case. Flexural testing is an interesting test to do, because any part that gets into the applications where there is more of dynamic actions, it has to either undergo bending or it has to undergo twisting. So, when we go for parts where different 3D printed parts have to become a part of an assembly, then it is necessary that we go through the bending of such parts. So, there are two ways. One is the 3-point bending and the other is the 4-point bending. By and large, we use 3-point bending, because it generally categorizes the right set of results that we are in need and we are in to conclude. So, D790 is the standard that gives us a certain dimension. Now, when you see these dimensions, these may be the dimensions which we may have selected for this task. It may not be only 127, it may be a range of some value, and from that value we may have made a selection. Sometimes it so happens that there is a thumb rule into it. So, the width that you select, that value gets into a thumb rule for the length or the other dimension. So, to set a minimum value of width, along with that a certain length comes into picture. So, the other day I had discussed that in order to achieve certain thickness of a test sample, you were required to place 12 layers of fabric. Yesterday in the we tried with 6 layers, I suppose, but for specific thickness that you required, you needed 12 layers. So, that became a limitation, that now all plannings you have to do with 12 layers. You cannot go for 14, you cannot go for 10. So, the study goes with those 12 layers accordingly. So, once you fix up certain dimension, the other dimensions comes into picture. Otherwise, why there would be 127? Somewhere I also remember that the dimensions came with 2 decimals, and then that was taken to the higher value, higher full value. So, those are things, but then we have a flexibility of a range of the dimension. So, we have to ensure that that dimension falls within that range.
Suppose we are having a gas turbine plate, and in the gas turbine plate we are putting the high pressure gas. In that case, it will be fixed at one end, and it will be bending also and twisting also. So, these two forces or two different forces, how it will be coming in this test, which is shown in the diagram.
See, the thing is, the part under application, if it is undergoing some sort of bending, you may have made that part following certain safety standards, right. So, we always take certain factor of safety. Now, we take it based upon what maximum bending would be encountered by the part. This testing will help us in a way that when a part of certain size is built, a certain size is fabricated, the standard size, when it undergoes bending, it behaves in a certain way. Maybe it fails at certain value, or maybe it does not fail up to certain value. We make two conclusions: either we decide that at minimum this value the part fails, that is something which I am interested in, or I decide that up to this value the part is not failing. Maybe I know that the maximum load which a part to be utilized in an application has to bear this much load. So, my interest is that when the testing happens, the part should not fail till this value. Beyond that, if it fails, whatever be the value, I am safe. But sometimes our requirement is that okay, part initiates to fail at this value. So, its failure is at certain value. You will have to make a design in such a way that this is extended beyond that. Now, how that happens? You will have to take those factor of safeties. How you take factors of safety? You find out the weakest link, and that dimensions you increase. So, when thickness of certain part would be fixed, when your thickness is say 3.2 and when it behaves in a certain way and gives you certain value, if you want to extend it and want to go beyond that value, this dimension is to increase. So, when we fix those dimensions, this is how our traditional design happens. We design some, we get some dimension, we test it, we find out that okay, our design is not safe, so we go to some higher value of the dimension. We again test it, it does not fail, so we say our design is safe, right. That is the traditional way in which we solve the numericals, the examples in our machine design. So, same way here, based upon the results that we get, we may now need to extend our designed part at a certain value. Getting me? So, if I am to go for a specific application, say in aerospace application, or maybe in turbine application, maybe in nuclear, whatever be the application, part maybe is a nickel alloy, part may be titanium alloy. So, under that situation, when it has to encounter so and so load, the same titanium when you use as a rod in the human body, it will undergo certain level of load, and the same titanium if you are using in some other applications, then it will undergo into some different range of loads. So, the thing is this standard test, and because these are standards, so now data books also have those values. So, they help us to decide a minimum dimension for the specific applications that we are working on. So, any of these standard test, ultimately whatever be the shape of the application part, your initial experiment would be with the standard dimension only, and it will become the base to fix up the exact dimensions of a selected design, right.
Sir, in your experience, have 3D printed composites, are we getting repeatable values? So, are we able to standardize?
No, not yet. I believe no. Those results are even if you remember in some of the graphs which we saw yesterday, the range was very high.
80 to 450.
So that is not something that is desirable. But then okay, when you have initiated it with repeated exposure, some results may come up, and that is why.
So, sir, it is
But why that comes into picture? Because the way you have put up all the layers
right, sir.
will have its effect.
So, the process has to be standardized to be able to get repeatable.
Yes, but then process, I don't see any major change into the process with the change in the manufacturer.
So, then, very practical question: how does a designer choose a composite part? For example, if we can't have a good way to design the failure, assume the failure of that part, why will a designer choose such a part, even though it has superior properties? So, what is the reason? that
I'll move into different territory, but I'll suggest a book. That book title is a textbook on design for additive manufacturing. Now he talks about lot of common sense applications when we are designing a component for 3D printing. So those thumb rules are something which you need to always keep in mind when you are designing a part. So those layers that you decide, your number of layer gets fixed because of your dimensions. Now in those layers, if you decide that I want to have 50% of fibers into it, so if the layers are 100, then naturally roughly 50, it may come out to be 45 also, or it may come out to be 55 also, but roughly 50 layers are your fibers. Now when 50 layers are of fibers, do you put them all together at the center, or you bifurcate them 30 here, 20 there, 20 there, everything changes. So based upon what imagination you have, you may fix up your internal structure design of a part to print.
But at least it will be repeatable for the same group.
For the same group, yes, but still I think that there the standard deviation is still high.
because sir, in the injection molding business, glass.
Some of the cases, I'll interrupt. In some of the cases, we repeated one experiment 5 times. We had thought of we'll have 2. In some cases, we had 3 repetitions. But then we had 5, 6 repetitions also somewhere. Why? Because the initial 2 had very wide variation. 3, a result came in between. Now when it came in between, I was not sure whether I would select this 2 or the other 2. So we made 5, and out of 5, with gut feeling we made a selection of 3 values. That is not standard way of doing it, but common sense if you use, that can always have an allegation that that is a bit of manipulation also. So yes, we require standardization into it, but
When the filament is on one side, I agree. Filament is not in the center of the file. Polymer is not around the filament. But the other manufacturing methods which you told, I think they should be.
yeah,
if
yes,
it is for the same
yes.
group,
But again, the curing also plays certain role. Curing. When we are using liquid resin, curing is a bigger culprit than the design. Where you cure it. So the same specimen which we placed yesterday on that particular table, if we just had put it close to a window where probably 2 hours of sunlight would have come over it, it would not have required 24 hours. And if the speed with which it gets cured, it would have its effect on the
3D printing it is.
yeah 3D printing. But when you go with an SLA process, again that becomes an issue. So there are many things to be standardized at a time.
Actually, sir, because in composites, injection molding is very commonly used. As
Yes.
you saw it for
Yes.
automotive parts,
Yes.
almost all plastics are composites.
Yes.
Some carbon filled or glass filled
Yes.
will inevitably be there.
Yes.
So clearly it has ample application.
Yes, ample applications, and there is a lot of scope to try to standardize it. But then there are multiple things which have to be involved at a time.
Which is why in the
So
starting you spoke about
yeah,
there are many factors.
yes, one at a time will not be possible into it. All things have to be taken simultaneously, and that probably is restricting the process of standardization at a time.
Right. The video is there for this?
Yes, but again that is not ours. Is it on? Okay. Now there is another interesting thing. We have two machines for impact testing. One can work up to 25 joules of energy, the other can work up to 100 joules of energy. The softwares, the suppliers are different, softwares are different. So their decimals are different. One has 3 decimals and the other has 2 decimals. So because of that, the graph that you get, they are totally different. So if you want to compare a part which as per the selection, if it is some way of printing with carbon fiber, even with glass fiber, does not get checked with a machine below 25 joules. So those parts if you check with the other machine, it will give you some form of data which you will not be able to compare. So even the way in which we have the softwares with the machine, the way in which those machines are used, the softwares that they have, they also give you a different perspective to this same job. Same job when you carry out on 2 machines.
This is why we have big factors of safety, because we are not very sure about this.
Yeah, traditionally Indians have always tried to play safe.
We have very big factors also.
Yes. So
But
that's
we have
why.
space program also. So
Yeah.
there's
Yes.
this
Yes.
factor of
Yes.
safety is not
Yes.
used.
Yes. Yes. Yes.
Previous few slides back, you told all your samples have been cut by using autogenous. In the initial stages, before fixing up the parameters, do you find any of the laminates getting delaminated due to high pressure or from the abrasive which comes out of it?
For natural fiber, yes, and for glass fiber, yes. We saw delamination.
So if that is happening, what would be your alternative?
I don't say that my answer is right, but my observation, our observation is.
But I also tried, sir, natural fiber and the carbon fiber. So
Did you put them together?
no, at the same time, one side, other
In
same day I can.
no, but they were separate samples, right?
Yes.
They were not hybrid.
Yes,
Hmm.
but that is
Hmm.
not hybrid, sir. It is carbon, glass fiber, different,
Hmm.
and jute, flexural.
Hmm.
I both samples I prefer as per the ASU standard
Hmm.
with conductivity
Hmm.
chemical properties.
Right.
And I didn't observe any kind of noise delamination
Hmm.
in samples.
Hmm.
Through abrasive water.
Hmm. Hmm.
I didn't find. I tried with other machine also,
Hmm.
but I had a failure.
Hmm.
Samples are damaged.
Hmm.
But through abrasive water setting,
Hmm.
I never get any kind of damage.
Hmm. Hmm.
By observing,
Hmm.
nothing I didn't face.
We'll see that sample today. What happens when we are working with VIRTM? The thickness of the resin above the fiber is very less. So at some places even fiber is outside. Resin may have reached there, but it is to such a level that you feel you touch the fiber also. So there is a weak point. So when you are cutting at that particular position, see we made the plate and we cut the samples out of it. If even a small trace of such part comes over there, then that fibers will move out. But in case of carbon fiber, maybe it might be some quality of the fabric. I do not say that this is what we have observed, I do not conclude it. But in case of carbon fiber, when you were placing it inside, it was remaining perfect at its position. There were no crease into it, just as we have those crease on the clothes, it did not have crease on it. But when it came to natural fiber and when it came to glass fiber, there were at certain positions they were not perfectly flat, it was slightly wavy. Maybe you cannot feel it by observing it, but when the resin gets infused into it, that slight crease will restrict the resin to pass from there. So you observe that the flow of resin is not perfectly straight line. It goes this way sometimes, it goes this way sometimes, or even it goes this way sometimes, depending on that particular position. And when it reaches the end, when it moves into that tube, we close it. So there would be one position where there is still scope that there can be more resin into it, but that small portion gets protruded outside, and because of that, and if it comes while cutting in that particular position, you observe pull out of the fibers.
If that is the case, definitely it will affect our testing.
There is another observation. Suppose when you are placing these 12 layers, and in the 12 layers all are carbon fiber, say for example, or all are glass fiber. So that is a neat fiber material. In another case, you place them together, carbon, glass, aramide, that way you put up. So the affinity which multiple layers of carbon fiber will have, all those layers they would adjust, and the way in which the aramide and the glass or glass and the carbon they would attach, it will not be same. Why? Because they come from a different roll, and in some roll you may have certain crease that will repeat at every position, right? Rolls come through transport, sometimes that rolls are pressed also. So when you place them together, you cannot do anything with that. So there is always a small space, a small void that happens between those two separate layers, and when delamination happens, that is observed there. Now when you are doing this manually, when you are adjusting it manually, often you are not able to place it with the perfectly stretched into it. So those may be the places where either some sort of pull out on the outer periphery, or maybe delamination at those layers that is observed. So probably it has nothing to do with the process, but probably because of the internal structure in which the resin gets infused, and the difference in the level of the infusion of the resin at different positions, probably that results into it. But no, we haven't concluded any substantial thing out of it. This is just based upon the observation, what you see. Yes, yes. Maybe in that particular case where Himanshu worked, he took 5 to 6 repetitions of all the samples, and for that those 6 were not taken from a single part. So once you make something, once you make a plate, you cut tensile part also, impact also, flexure also from it. So one plate will give you one or say two samples for each. Had I taken all 6 impact from the same plate, maybe I would not have got difference into it. But then we took another plate, we made another one where again we got one impact, one tensile, and there you incline the position. So one sample comes from 090, other comes for 45. Getting me? So that way we tried to do lot of randomization into that. So if you see the paper, you will not see a single trend. So in abrasive water jet we observed that, but that may not be because of the only abrasive water jet process. It may be because of this inherent noise that you have in the fabrication process. Even we tried to iron that. Are we able to remove that crease or not? An MTech guy did, because he worked only on natural fibers, and so we thought, let us do it. What at the most it would burn, but we tried doing it.
So basically, this technology is grinding like how we go on.
The same way, the way the same iron we used, which I used at home, the same thing we used.
No protection.
No. See, when it is jute fiber or when it is say flex, they are as good as cloth only. You can try doing it. So there are many observations which you can put on a paper. So you do not have anything to back up those observations. You can only discuss within, but you cannot put it on a paper. Impact testing is another interesting thing that we can carry out. Are we going for that testing now? So again, there are these dimensions. You see 31.8. So that may not be the defined dimension, but it may come from some other dimension. When you define thickness, when you define width, accordingly you may be defining the length. So total length comes out to be something, and accordingly those things would get into it, right? Here you see these dimensions are A, B, C, D, and again D, if you see over there, D has R into it. So the dimensions are interrelated, and then those dimensions should fall within certain range. That is a requirement. Again, there are some standard where you need to make a notch. In some cases, you don't. No, even I thought when that comes down, it makes some noise, right? When it comes down, before it strikes, when the movement starts, you release it.
Sir, it is the noise of that. It is able to move quickly तैयार.
Yes. So when you release it, at that time it has that noise, and then when it strikes, but then what was the third one?
We have to stop that particular
Manually. That is not standard. So this one is the machine which has which can be used up to 25 joules. Hardness, usually we go for 3 different sets of hardness testing depending on different conditions. Often this goes with the facility that we have. So in case of Brinell hardness, our indenter is a sphere. Our indenter is a sphere. So you measure 2 values of diameter of indentation, and it gives you the value. In case of Vickers hardness, the indenter is replaced. It is pyramid in shape instead of a circular one. Instead of a sphere, it is a pyramid. So there the diagonals are measured. Diagonals of the square are measured. So if it indents less, the value of D is reduced. If it can go for, if it is a softer material, it will indent more, and so the value of D will be more. So those 2 values are measured and calculation is done. Now we don't need to do, suppose I believe that when we did these experiments during our BTech first year, we had to observe it, and we had to also measure manually, and we had to take those values and do the calculations. But now machines do everything by themselves. They do not rely on us.
How relevant is hardness testing for composites? Because hardness tests are surface tests, and composites depend on what surface is exposed will kind of give you hardness. So it relevant firstly as a test?
See, for metals I do not have a proper answer, but I will try. When it is metal matrix composite, I have seen that people trying the micro hardness testing, because the particles that are dispersed, say silicon carbide or similar any other particles that are spread across, they probably would restrict the indentation. So there they go for micro hardness test. Now when it comes to polymer based material, again what sort of mixing that you have done. Say for example, we did not try on any of our composites, be it 3D printed or be it the other process. But in case if you do it, then it would largely depend upon how the polymer hardness comes because of what reinforcement you have. But we did not do for any of our materials, thinking the same, that it would be same as what polymer behaves. So for polymer we already have the data. Yeah. So there is no point in doing micro hardness also, and there is no point in doing the regular hardness test also. But for metals, they go for micro hardness testing. They go for even smaller depth of measurement. And here you are required to do some calculations, but again the nowadays softwares do it. This is interesting because you go for two different levels of indentation, and then you in that figure if you see, the the D is the value that you are interested in. So initially when you put up the first one at the first layer, when it is FO, it goes up to depth A, and then you add some force into it, it goes up to B, and when you remove that secondary force, there is some retraction, there is some reduction, and so that reduction value is C. So D is something that we are interested in. This may be something which may support when we are going for parts with reinforcement, but we do not have this setup. Thermal analysis is an interesting part. Up till now we were not that much focused with this study, but recently one machine we got in another department. So since last 2 years we have been trying at least one sample and getting some information out of it. It is adding some more information to our knowledge base, and of course to the publication also. So there are many tests in fact, but there are 3 tests which are being widely included. One of them is TGA, thermogravimetric analysis, TGA. In this thermal test, the machines are so sophisticated that you can fully rely on the results, and the other thing is there is minimum involvement from the operator. So reliability is increased a lot. So when we go for a TGA test, our intention is to study the weight loss of a part with the temperature. So we have some setup wherein we put up the sample in particular way, a small sample in particular way. It is placed enclosed in a heater, a furnace sort of thing, and then it is the temperature is given regular course of time, and because of that heat, whatever is the loss of weight, initially you have measured the weight, later on you measure the weight, and that loss of weight will give you some idea. So this goes with the thermal stability, the temperatures at which some sort of changes come into it, decomposition comes into it, or how the part gets degraded. Degradation comes with, because there may be moisture into it, there may be that removal will also result into loss of weight. sometimes the part may even partially burn. So, those things that come, they are represented through a thermogram. So, here what happens is, as you increase the temperature, there is reduction in weight. This is a graph for a particular set of polymer. So, if the weight is say 10 grams, so percentage wise it is 100% right now, and then once you start hitting it, the weight starts reducing, and initially there is some loss. This curve denotes certain aspect of it, then the steep curve also denotes something, then it denotes something else, and then it becomes stationary. So, whatever loss that comes into it, that is represented by a curve, and we are able to make certain judgment from the curves that come on this curve.
This should be before my presentation. Yeah.
Actually we had, that was our plan. Our sequence was right, our actual sequence was right.
Your presentation had that chart also. Anything else interpreting the
Yes, in any sort of system where you are using a machine only, interpretation is the only thing. Even in SEM, you would see many images, but they are left without interpretation. In the papers also, if you see,
believe me, it happened. Kunra cannot understand.
yeah.
many times.
And the thing is, if I make certain judgment, this is a hard fact. I make certain judgments for my graph. You yourself do not know how to interpret it, so you have no other option as a reviewer but to believe what I am saying. That happens.
Very difficult to prepare the graph,
Yes.
the thermographic
Yes.
analysis, and to make the details explanation. Yeah.
So interpretation. I'll tell you another example.
There are a lot of
When
connections, yeah, with the other properties you have to explain with the reviewer request. Yeah, well, it's so
yeah, but if the reviewer puts up a question, then you include reply to it.
yeah.
Otherwise, it goes unattended, and then thousands of people refer it, and then they copy.
And it continues.
See, you take example of a statistical process response surface methodology. When you use a software to you feed your experimental data into it, immediately it will give you a analysis of it will prepare a model, an analysis of the model. Then it will give you a linear equation, 4, 5, 7, 10 lines of an equation, all parameters included, and it gives you a 3D plot. People represent it. Many times I have put up such question in review or to the exams that I conduct at our place for our PhD seminars. Nobody tries to understand why you get certain graph, how to interpret a particular curve on a 3D graph, where you get from RSM, and why you have certain way of those experiments in RSM. But this is a trend. You put up results, put up the ANOVA model, put up the equation, and then come up with this is the probability of the results may go wrong. And when a reviewer, it comes to a reviewer also, probably everybody will not be knowing the statistical analysis. So that goes unattended, and because I get to see a paper with these things, then I also do it, and when I do it, maybe somebody else also does it. So this is how that cycle goes on and on. and everybody puts up and nobody knows it. That is a hard fact as far as certain trends in research are concerned.
Actually, some people are afraid to discuss also. Some people are afraid to discuss that they think it might get rejected. Just put it, let whoever want to interpret, let them interpret.
Because software will do all kind of calculations.
It will give you everything.
Manual calculation if you do, they will understand everybody. So this is software do all kind of calculations.
Writing a
Yes,
paper
sir.
discussion is the
Yes,
tough part.
yes, yes. Yes, that is true. Yes, sir.
Sir, my question is, suppose we are doing this experiment, and what we do, we proceed only to some temperature where we are saying that high volatile material will go up in the environment, and we stop the testing. And what we do, we again decrease the temperature of the material, and again increase the temperature of the material. Then what will be the possibility that again we will be getting this high volatile material again will be going to the environment?
There are two parts of answer. The first is, I do not know if that can be done or not, because the standard procedure is you place it and you allow it to go up to the temperature up to which it can melt. So you go up to that temperature and then you come back to the normal situation. So you need to go there. By the time you go there, these stages will come. I haven't come across a situation, and maybe I haven't tried it, that wherein we say for this particular case which goes up to 800, 900 degrees Celsius, let us go only up to 400 and stop. Then allow it to cool and then again restart. So when you restart it, probably there is no volatility into it, right? This is what you are asking. But I haven't come across such anybody doing that. Maybe when you put it, it has to go up to full cycle of that test. Otherwise, it will not be this particular test. Maybe interesting. Let's see if that can be done. Maybe we'll try it.
Because
What
you see
happens?
that, we are supposing that high volatile material have gone, all of the material have not gone into the environment. Some is there.
No, at certain temperature it will naturally go, every material, yes.
But at
If you do not go up to say 300, say 200, 210, if you restrict, then probably you will restrict yourself somewhere here only, right? You are saying that, right? Maybe 250. And then you come back and again you restart. So what happens in that situation? Interesting, but no, I don't think so anybody has tried that. Maybe we can try, yes.
Sir, how important is TGA for pure metal, MMC and CMC? Because there
TGA that I have referred, they are for polymers, mostly for non-metals, I suppose. I am not sure, but I have seen it for non-metals. Have you come across for metals? Ceramics, yes. I'm not sure. Okay, but fillers or ceramics, full ceramics. Okay, for powders.
solid samples also, we need to cut 50 milligrams.
Okay, okay.
We are used for clay sample.
For clay we have done that, right?
Powdered form of clay, 10 to 5.
What temperature did we go up to?
Sir, it varies.
Based on the melting point of the material, sir.
So up to melting point, maybe you need to go. You cannot stop the process somewhere in between and then. Yes, 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 yes. This is another thing, DSC. Here the study is about the heat flow, especially when there is phase transition. So how the heat flows, does it get stored, does it get removed, does it flow promptly? So those studies come under this. So here we are required to calculate when we take a, say for example there is a sample that we want to study, there it has to be compared with a reference material, and because of that reference whatever heat flow happens, that is what is studied over here. So when we try to change a sample from solid to liquid, or when we are studying certain physical changes into it, then at that time whatever flow of heat takes place, that is included into it. So, this is one such setup wherein there is one sample, the other is reference, again it is put up in an enclosed situation, and there the test is being conducted, and the flow of heat and the difference in the temperature is measured, and here with the temperature this is what is observed, the heat flow versus temperature. So, these are the changes. Glass transition takes place, then crystallization takes place, melting takes place. So, at different conditions of the phase, the flow of heat is studied. Again, these thermograms helps us to make certain specific conclusions. Personally, I haven't included this ever in any of our studies, so I haven't interpreted it for any of our results.
So what is the reference material?
Reference material specifically I do not know. Yes, sir. Yes.
Yeah, I can send the reference.
Okay. 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 Okay.
If you want.
Of the polymers. This is the aluminum band to measure the dynamic scanning calorimeter.
There are about 10 videos by this group, and they are really very interesting. I do not know who the person is, but he is explaining very well. Huh? It's on YouTube. Yes, I can share the links. I am going to share many of the things.
Here is the DSC instrument. We bring the sample seen inside of the aluminum band. Open the cover of the DSC instrument and get ready to put the sample on the right side.
And depending on what sort of study we want to go for, maybe we need to create a nitrogen environment, and in cases we also allow regular air. Sometimes we need to avoid oxygen. So that choice goes with the type of material that we are working on.
Then we are ready to start the DSC analysis of the sample.
Depending on the thermal properties of the sample you want to measure, you can set the software on the tests you want. Standard, for the determination of the total heat of reaction, or the modulated DSC, also known as the MSDC, for such properties as the TG value, the melting temperature, and the degree of crystallinity.
The DSC analysis is done under nitrogen gas to minimize oxidation reactions and obtain only the thermal properties associated with the polymeric material.
The glass transition temperature, TG, is the temperature at which amorphous solid becomes brittle on cooling or soft on heating. The degree of curing determines the amount of the sample, percentage weight, that is cured or polymerized. The degree of crystallinity is the amount of the polymer that is amorphous and the amount that is crystalline, percentage by weight.
The third test is DMA. Again, we haven't tried this on any of our samples, but dynamic mechanical analysis is for viscoelastic properties of a sample, and as a function of temperature or frequency and strain amplitude. Here what we try to do is, I'll go to the figure only. So this is that setup. Here the part has to be certain dimension, and that has to be placed between, that has to be held properly, and then it has to be heated. And when the temperature, when we are heated, when we place it in between these fixtures and when we pass it through this heater, then sometimes it is, in some cases we prefer to give it tension or compression, sometimes we prefer to twist it, sometimes we prefer to bend it. Under that situation, what response it gives, the strain that response it gives, that is being measured, and that helps to measure some of the dynamic properties of the part. So,
under a UTM also in a chamber.
okay.
That temperature range is different when you compare to DMA?
No, that would be different when we are using it on a UTM. What do you call that setup that you enclose, that chamber? We had planned to get that one, but funding restricted. You have that separate chamber wherein you can control the temperature. So that huh? No, what do we call that?
Environmental chamber?
No, it is a very good name. I am not recollecting it right now. Okay, but here what we do is there are four different stages that come into the sample with the temperature, and all those stages the material has a different structure. Initially it is a polymer may be rigid and brittle. When it goes into at a higher temperature, so naturally it becomes flexible. Further, when it goes, it undergoes large elastic deformation, and then at the end it is almost becoming in the molten state, in the viscous state. So there are few things that we observe. The storage modulus, how the heat is stored by the material. The other is the loss, the blue one, the loss modulus, how the stress is reduced inside the material. So that talks about the loss part. This has something to do with the ratio of this part, but I am not clear about it at the moment. So these are certain results which give us the information about how a part when it gets into the transition phase from solid to say viscous state, how does it behave. That information comes through this phase change of the part through this test. Again, we haven't worked on it, so I do not have my own results for this.
Inside of the dual cantilever and the DMA instrument, we just put the sample there inside and tight it up, the screws of the dual cantilever in this fashion, and use this special screwdriver to tight it up. You tight up until you hear the clip, which indicates the right pressure on the sample inside of the dual cantilever. Once the sample is properly mounted in the dual cantilever of the DMA, we just close the furnace of the instrument and go ahead to the computer.
The DNA applies force sinusoidally at several frequencies over a temperature range. As the sample deforms, displacement is automatically measured. The magnitude of the applied stress and the resultant strain are used to calculate the stiffness of the material under stress.
Once all the parameters have been set up for the DMA analysis, the test is stopped, and at the end, you will end up with the different values of the samples, such as the storage modulus, loss
storage modulus is the measure of the sample's elastic behavior, while the loss modulus is the measure of the sample's viscosity behavior. The ratio of the loss to the storage is the tan delta, which is
Loss to the storage is 10 delta.
Sir, I have a question.
They are doing good task, this Australian university.
I don't remember being taught this any time during BTech.
Probably we did not have these machines then, at least not at my time. I am not sure about you.
Yeah. So, are they being taught now?
No, we just touch over it, no details. So yes, in material characterization subject we have this. They are into detail there, they are chapters. But the thing is, we still touch upon it, that this is the machine, it is used for something, and this is how that interpretation happens. In fact, we don't have these setups now.
Sir, polymer seems to be very important test.
Yes, yes.
Yeah.
We have been putting it for our requirement since last 3-4 years, and hopefully we should get the fund soon. So fatigue test, the interest is to know how a part behaves under a regular long term loading repeated condition, and so how far its durability is and how does it perform under such cyclic loading situation. That is what we are interested to know. So you can apply it under different situations, maybe tension, compression, bending, and those choice depends upon what application we intend to study on. So there are the ways in which we can interpret the graph. It is divided into 3 major sections, and based on that we are able to predict what would be how many cycles will be the normal service life of a part. So if we are going for very high loading situations, so naturally the strength part, the short term strength is high. Number of cycles that you will undergo would be a lesser number. If you are able to have something which has very high endurance, so it will continue for a longer duration of time, for more number of repetitions of cycles. So based on this we will be able to come across certain value of n, where we are able to, because this is the endurance phase. So when we come to this value, we will be able to find out certain values of n, which will denote how up to what repeated cycles this would the part would perform well. So that helps us to, so sometimes these tests go for hours and days together, and having such a setup is also there are many industries in Surat who have this, like L&T. Conductivity, yes.
Fatigue strength, you mentioned fatigue strength Z.
Let me go to that. Yes.
Specific formula. Actually,
Maybe it would be having some formula, yes.
Formulas for metals,
Hmm.
aluminum, steel.
Then it must be there, I am not sure about it.
I am referring to anything.
Formula for calculating the fatigue strength for polymers, right? It must.
As per the bending equation. So 32 m d divided by
Yes,
pi d cube.
right.
This is the general formula for all kind of materials.
Probably it should be similar to that, but I am not sure about it, because fatigue is something which we haven't attempted. So
the shape is a big influence.
shape of the standard part, but that shape will go with what sort of application we want to target. So
There are also variations, but those only for the metals, not in case of polymers, as I know.
okay. To have its own formula, but probably it can come up if there are results, but then that is a very tedious and long term.
When I was in Godrej, they used to do fatigue testing of lot of items. So they used to simply load that part and put it for fatigue.
for
That's how
few
they-
days. Yes.
So there's no way to. When I had asked the same question, they said they can't design for fatigue. They have to test the part for fatigue, and that's how they.
In fact, the L&T does the same thing. They suggested that if you have your own machines, then we can outsource our task, and you run the machine 24/7 for us. Yes.
So they're actually trying. They're doing the cycling of the part, and then
Mm.
especially for.
So you mean to say that there may not be set equations for it?
No, no.
Even for metals,
Yeah, even for metallic parts, they were doing
like
those
as
tests.
Professor mentioned, the size,
Size, the shape.
you cannot bring every parameter into the form.
Mm.
Better do the exercise.
So
Mm.
for metals, I believe there is standard circular rod and
Yes.
there is a flat piece where those tests are there.
But for application,
So depending on that application, you will have to make a selection of that shape, and accordingly the test
You
will
have to
go.
do the test for that part
Mm,
itself.
no, they make the part, final
Mm.
part, and they do the test.
Mm.
Rather than making according to a standard, they make the part final and then test it, put it at the life cycle.
Acha. But then that would be for specific material and specific shape.
Typically for shafts you have
So if you change the shape, if you change the material again, that equation will not work.
yes sir.
So.
Similar means okay.
Mm.
That's what I told for shafts.
So if you change the material and once you change the shape, then there would be minor change into it, but there would be some change.
The shape of the material, the moment of inertia will be varying.
Acha.
So accordingly the process will vary.
I'm not that aware about that part.
Biomedical example.
Mm.
They are also
We
doing
directly put the implant, 5 lakh cycle, 10 lakh cycle. We hope the implant should work for 10 to 15 years. So we calculate per day how much time we load the implant, and we do it for 5 years, 10 years, just 5 lakh cycle, 10 lakh cycle. So we do on the actual geometry of the implant.
Okay. So then there may not be those results will not be able to give us a standard equation for it, right?
Even if the equation
So-
is there, nobody is going to use it.
Yes. For each and every shape, you will have a different result and may different way of interpreting that result.
Different types also the cycles.
yes, the cycle
Different types.
low cycle or high cycle.
Yeah, low different.
Okay.
Different scenario.
So interesting. What if the part does not break after that many number of cycles?
It's a great part. You should under engineer it.
And suppose if it breaks at the say 75% number of cycles as per our target, so how do we interpret? Suppose it is for 1000 cycles, and if the part breaks at 700 cycle, so how do we interpret that?
You need to change the material.
So again there is a range of way in which we may interpret it, no? We may make conclusions out of it. Hmm.
There is a very interesting question you asked regarding the glass tungsten filament bulbs. So when the bulbs were invented, there were 3 or 4 companies. Those bulbs used to never go off 60, 70 years or easily their life. So they started engineering filaments of thinner diameter so that the bulbs started failing, and it was a cartel. There was a cartel, and all the 4, 5, including Philips company, they started making thinner and thinner filaments so that bulbs start failing after 5 to 10 years, because otherwise the business is
This particular incident is discussed by Philip Ross in his textbook on Taguchi design of experiments. He has come up with this example of filament bulbs and its life and how that is correlated with.
That is probably one of the rare cases where they engineered together to reduce the life of a part. Normally we want better.
Now, if it works for life, then you and bulb will go together only. So, Then the next is I'll આપણે પેલું થોડું ડીલે કરાવવું જોઈએ. Now I'll go through this conductivity test a bit faster because I also want to go through the qualitative testing part. Okay, thermal conductivity test. What we try to do is here we put up a sample for testing wherein we subject it to the light source, laser source. So there on one side we are providing this energy through lasers for a very short duration and with very high intensity of this energy, and when it moves on the other side we make that measurement. So that flow helps us to study the conductivity indirectly because we study the diffusivity into it, and that helps us to make a conclusion about the conductivity of a part. So the flow of the heat will help us to make a decision into it. In case of electrical conductivity, there is a 4-point probe method wherein the sample is connected with four probes. This one is that slide. Acha.
In MEMS we do that.
Okay. And so in that case our intention is that at different positions we, just as we use a thermocouple and we measure the difference, the same way we measure the difference into it. So at some place there is a non voltage and at some place there is a different voltage.
VI characteristics. I may be wrong. I think we get the VI characteristics. So what we do in MEMS industry, we make diodes and transistors. Okay, so we need more. So we give two voltage across two terminals and we measure
The other on the other
and
side.
we keep one thing as constant.
Constant.
And the base voltage and conductor.
Right. And that will give us a trend line, and based on that, yes, and based on that we make the
And we tell that this can be a diode, this
yes,
can be a transistor,
yes,
this can be a
yes,
switch. So
yes. So conventionally we can put up on a graph and then we can make that measurement. That is always a practical in electrical engineering. But the machines, they give you the direct results. You don't need to do that
Under a
part.
microscope, we have to just
Yes.
touch the, using the probe, we have to
Yes.
just tell where we have to apply the voltage
Yes.
and where we have to measure.
But that would be for the micro part, no?
Yeah, for this is a macro part.
Yes.
So
So
you
macro,
you don't need a
yes,
microscope.
yes.
But again, they do this under liquid nitrogen, some ambient temperatures also.
Mm.
Cryo testing.
Ambient temperature probably, yeah, you need a controlled condition environment. Okay, then I come to this last part wherein we want to talk about certain qualitative techniques. Now these are those processes which help us to make certain conclusions, ranging from a small part to a very small part. So up to nano dimensions also we can utilize this. So these are classified, these qualitative techniques in general are classified in 3 ways. One is using certain microscopy, then going through the spectroscopy and the surface profiling. Now generally when we go for qualitative study, we do 2 things, either we observe or we touch. So any decisions that we make for a qualitative term, we may feel, okay, this page looks bright and this page looks dull, this is white and this is off white. So that is an observation. Sometimes we touch the surface, we touch the cloth and we decide that this is a smooth cloth and this is a rough cloth. So we make our decisions as far as quality is concerned either by seeing it or by touching it. So these processes are also, they either see something or they touch something. So we divide, so there are certain processes which are observing it, and then there are certain processes which use a probe to touch and give us the result. So scanning electron microscope probably is the first machine that took us to the nano level of observations, and then many other machines technologies followed. I'll skip some of these things because these are known. But in this case what happens is what we try to do is we try to avoid physical lenses, but we create lens through creating certain field. And when those electrons are, instead of using the light, we use those electrons. The electrons, when they strike on our sample, what happens is either those electrons will pass through it, or they may reflect back, or what they do is they create a reaction, they do something inside with the existing electrons, and something comes out of it. So, there are three different distinct way in which electron comes into it. These are two different setups. Both S3000N is also there with our department, and this machine is also there with us. So, I'll skip the construction part of this. But then the signals that we get, one of them is the secondary electrons. Secondary electrons come through an ionization process that takes place inside. So, what happens is when these electrons that strike on the surface, they get into the structure of the molecules of it, and they create ionization, and those new electrons, they are second level of electrons. So, they are secondary electrons. Some of the electrons, when they strike on the surface, they scatter back, they return back. So, they are considered as the back scattered electrons. And there are third type of electrons, those are X-rays. So, when this electron beams gets into it and instigates a new electron from the part to move back. So, yes, that electron passes away, but it gives a chance for the existing electron from the part to move back. So, that comes out in the form of X-rays, and all these three are measured. What we get is we get the exact structure of the part. So, we are able to make the measurements. So, that way it supports, we can go up to very high resolution, say up to almost 3 lakh times of magnification. So, the smallest impression that the part may have, that is also made visible. So, these are few of the such observations. Is it playing or not?
Working of scanning electron microscope. In this video, we are going to see about working of scanning electron microscope. Internal parts of scanning microscope.
The S3000 which we saw there, that requires vacuum generation into it. So, it takes about 20 minutes or so, 15 to 20 minutes to generate vacuum. And if the task is very simple, within 5-7 minutes you may complete your task. Again, it needs 20 more minutes to remove the vacuum. But as compared to that, the other tabletop microscopy is a lower version. It does not require the vacuum. So, that time can be saved. It is only 1/10 of magnification which the regular SEM has. But even if you are able to go up to 3000x for our applications in say mechanical domain, it is more than requirement. So, 30,000x we never explore for our applications. Okay, the next is transmission electron microscope. As the name suggests, this gets transmitted. So, here our requirement is that the electrons will have to pass through the sample, and that has to be collected somewhere. So, it will generate an impression somewhere, and that impression is being utilized. So, as in case of the previous thing where the electrons had to scatter back and it would create an impression, here the requirement is that electron should pass through the part, on the other side it has to create an impression. Surface level. So, it will be able to give you the entire entire topography of this part, yes. But and that is why you will need to make those samples thin. Sample preparation would be a difficult task, and it will need more of the expertise into it. wherein in case of SEM, if whatever the sample size it can accommodate, you will be able to create. Of course, you need the surface treatment into it, but that is an easier task as compared to the sample that you need to create for this process.
In SEM, you can also know the elements of atomic number of.
Yes, yes. Even say for example, in the metallic components which we generally check, what we do is, of course, we have one faculty member who is good at interpreting this. So I usually take her help for interpreting those things. But as far as machined parts are concerned, if you have machined through EDM or if you have machined through other processes, what we try to do is we see how impressions are generated on the surface. So that when you magnify, when you see it, you feel that there are only cracks, but really they are not cracks. Maybe they are different levels of layers which are placed over one another, and their boundary seems to be the cracks to us. So again, in such cases, the interpretation is a very critical thing. So in this case, the difference which I wanted to show is that here the part has to be very thin, and it should allow the electrons to flow. It only takes time. The process does not take time. Sometimes it so happens that when you want to have such sophisticated setups, maintaining them is a bigger issue than procuring them. There are, yes, they have it. Now, when we want to go for chemical composition and checking the chemical composition, we pass the infrared light through the part using the setup of FTIR. So here what we do is we get the dimensions at the structures of the molecules and the chemical compositions. We utilize in this case in case of this process we utilize the magnetic properties of the nucleus. So we create a strong magnetic field, and we try to observe the molecular structure through it. Again, this probably has I think you may be better person to discuss this.
Yeah, it's like MRI. In MRI we form the image, but here with the currents, the RF antenna, what it picks up from that we take that.
But eventually what you get is a graph, and that graph helps you to interpret what type of composition it has. So suppose if you are placing say a human bone, then it will give you the composition of it, or if you place a metal, it will give you composition. What would be the parts that you would work on?
Yeah, generally what we do, when we do a lot of synthesis, so we just want to see how much, like when we do multiple stages of it. So in each stage we put it to the machine and we see how much percentage has come, and is there any change. It will give the percentage mostly of the chemicals.
Okay. And what would be the
more of functional like aldehyde,
yes, yes,
those things.
yes.
Amines. Here it is more of the elements.
But again,
Elemental value, elemental composition value
Again, we are basing on the hydrogen proton.
okay.
With respect to that, we just oxygen. It is for each element how it responds differently to the polarization given by the magnetic, and how it is responding to the RF pulse. So every element responds differently.
Okay. In fact, there is one lab in Anand that was set up with DST support at Sardar Patel University. All that you can think of is there under maintenance. Professor, you were adding something to this?
No, about the nuclear magnetic resonance.
Hmm.
I remember that I sent a paper the nuclear quantum
So did you do it?
But up to the end, he accepted without NM testing because in my opinion, it's rare, these properties in our case, I mean, now in polymers, I think.
Mm.
Yeah, was, but it's very difficult in our city. We have not.
Geomagnetic rep.
So I'll still further extend my speed now, because I fear then. Okay, so now this is something about touch. Okay, so the simplest thing is to measure the surface roughness by using stylus profilometry. Then the optical profilometry, there also we measure the surface topology, but again that is through the light. We observe it and we measure it. So this is something similar to the vision measuring system. So we'll show this, right? So this is we are going to see maybe today itself. So I'll skip this. Now the last part that I come up to is scanning probe microscopy. So here what we are trying to do is we are trying to use a physical probe in two different ways, so that it tries to reproduce the surface feature, surface texture. So this is done in by two things. One is it scans the surface. So when we carry out scanning, whatever is there on the surface, say if we are doing a paper scanning, then whatever is observed, that is reproduced. Same way here also, scanning, while scanning it takes care of a x and y surface and it gives you that impression. When probing is done, you have a physical probe, a tip which moves and it measures the x z movement, and accordingly it gives you the feature in the x, y and z direction. So under scanning probe microscope there are two different types of microscope. One is the scanning tunneling microscope, which studies the surface topology of conducting materials, and then you have atomic force microscope, which is used to study the topology of insulating materials. So basically the task involved is to scan and then to probe, measure along x, y and z, but the difference is in the way, the major difference is in the way the tip is arranged, the tip for the z movement is arranged. So in case of the scanning probe microscope, the tip is brought close to the surface, very close to the surface, but it does not touch. It creates a sort of attraction between the atoms, and because of that it is also being used to displace the atoms. So in a way this is also used as a nano manufacturing technology. So your intention is to scan the feature and to observe the feature, but while doing that it works at such a level of angstrom that it is able to replace atoms. So there are few images which are usually used with this, wherein those atoms are replaced and somebody has wrought IBM with those atoms. So that image is always viral when people discuss this, especially BTech students use it for their presentations. So the thing is, in case of these two, atomic force microscope and scanning tunneling microscope, in one case you want to measure the interaction force between tip and the surface, and where in the other case you are trying to measure the electrical current that flows between them once they are brought very close but slightly apart. So there are two ways in which we do this. In case of STM, the sharpened conducting tip is used, and in case of AFM, a cantilever sort of thing is used. So because of that cantilever, now that cantilever is also not that too big, but because of that it is able to sense the Z feature, and that helps to give you the X, Y and Z positions. So there is there is a physical contact that happens in case of this cantilever AFM, whereas in the other case there is a force of attraction in between it, there is no physical contact happening over there. So, oh. So, there is a force of attraction
What is also you need very clean sample.
yes.
Very
One of
very
one of my friend once loosely said that it is just like moving to a sweet shop and just lifting a laddu when the owner does not know it. It is that simple. An atom is lifted and it is shifted.
macro level it is.
So, I will move to next. So, this atom is now being shifted, while the intention is to measure, but while that, because of that force of attraction, the atom gets attracted and gets shifted. So, there are few papers where this setup is attempted to carry out nano machining. So, your intention is to move the atoms. Animation looks very attractive, but it is not that simple task, and probably it is even difficult to observe.
I have come across like tweezers,
Hmm.
the optical tweezers to
Okay.
something similar or
No, I don't know about that.
Contact mode is the most basic mode of atomic force microscopy for measuring topography. In this mode, the
Bas,
cantilever scans while applying a constant force onto the surface of the sample. As the tip approaches close to the sample, the tip eventually contacts the surface. Once engaged, the cantilever bends upwards proportional to the amount of applied imaging force.
So, because of this deflection,
As the tip passes
the
over
topography is
constant
generated.
temperatures, the cantilever
So, here the thing is it touches the surface.
The deflected laser spot on the position-sensitive photodetector will move due to the change in contact force. The feedback loop responds by moving the Z-scanner to restore the initial cantilever deflection to keep the applied imaging force constant. By tracking the displacement of the Z-scanner, you can ultimately determine the surface topography of the sample.
Okay. So, we end the session right now, and we can have more discussion over it, and questions during our lunch break, because we are already late for today. So, we will move. Sorry for taking more time.